welcome everyone. I'm going to be talking about just a couple of applications of graph theory to machine learning. Um, my initial my initial goal was to go over every possible application of graph theory to machine learning, but then I quickly realized that that's not the best idea. So I'm just going to be focusing on um, basically a couple of papers that are more focused on leveraging the structural properties of graphs. They like things like spectral graph theory and stuff like that, in order to improve learning on graphs. Yeah. Okay. So just an introduction. If you don't know what a graph is, basically, I guess the formal definition of a graph is just a set of vertices and a set of edges, where this set of edges is just a subset of all of the possible pairings of vertices. So we're going to look at this example and use this to extract some information from a graph. So we have So if you're not familiar, the circle things are vertices or nodes, and the lines between them are edges. Um, I guess the most simple and inherent algebraic representation of this would just be the adjacency matrix, which you guys have probably seen before. Um, Essentially just a 4x4 matrix because we have 4 vertices. And each of the rows and columns represent the vertices in order. So 1, B2, B3, 4. So in this case, this is basically just defined as each of the elements in the matrix represent the pair of vertices that correspond to that location. And then from that, we just put a 1 if the two, nice, put a 1 if the two vertices are connected and a 0 if they're not. So in this case, we have for example, well, since this is just a regular graph with no variations, each of the vertices are not connected to themselves, and then we just have for example, V1 connected to V2, V1 connected to V3, so on. So it's something like this. Okay. So I guess this is kind of why are graphs fundamentally important? As you probably know, graphs can represent a lot of different types of data. For example, social networks where each person or entity is represented by a vertex, and the relationships between those people are represented by edges. And then another type of graph is a bipartite graph, which can represent recommendation systems, which is, if you don't know what that is, basically just vertices are partitioned into 2 sets, and the edges only go in between those sets. So if we have 2 vertices in this set, they can't be. And then graphs can also represent things like traffic and transportation networks. Basically, if you have vertices representing cities and then edges representing the roads between them. This also kind of introduces some ideas that are also important sometimes in machine learning, which are weighted edges and directed graphs, basically just assigning extra information to the graph. So for example, on this graph, if we had let's see, we assign this edge to be of weight 3, this of weight 2, 1, something. And then we could say a certain path from one vertex to another vertex has a certain length based on the weights of the edges. And then we can also have something called directed graphs where basically in this representation, this is kind of the same thing as saying, for example, if we have these 2 edges, there's an edge between them. Let's call them A and B. We have A is both connected to B and B is connected to A. But then if we have a directed graph, we can say there's only an edge between B connected to A in that direction. Yeah, so these are some more structural classifications of graphs. Because it's such a simple data structure, yeah, it's kind of a little bit deceiving almost because there's just so many different structural classifications that we can extract from graphs. One of them is connectivity. So I guess like the extreme example of this would be a complete graph where like every vertex is connected to every other vertex. And then the other extreme would be like there's no edges, like nothing is connected to each other. So that's a pretty important concept in terms of like measuring how well connected a network is, for example. And then we have sparsity, which is the amount of edges in relation to the amount of vertices. So a sparse graph would have not that many edges in relation to the number of vertices. And then something else that can be pretty easily measured algebraically is cyclicity. So like this is a cycle. Um, yeah, say if we have like a larger graph like this, then it contains a cycle, and then graphs that don't contain cycles are trees, which are also used a lot in CS. So you guys are probably familiar with that. And trees are also like pretty easy to distinguish algebraically, based on like some of the methods, which we'll see later on. And then bipartite graphs, I already talked about. Bipartite graphs are kind of like a subset of ways to partition graphs based on proper colorings. So bipartite graph is essentially just a way of partitioning a graph into like two colorings. And more generally, a proper coloring is a coloring so that, so I guess I can take this graph, for example. If we like assign colors as numbers instead, we could say like, this is 1, this is 2, this is 2, this is 3, something. And the rule of a proper coloring is that those two vertices with the same color are made. So, yeah. And like, yeah, there's like a whole, I guess, subsection of graph theory that deals with like chromatic colorings and like algebraic representations that can be derived from all of the possible colorings of the graph. Yeah, okay. So let's go a little bit deeper into encoding information based on matrices. So we already went over the adjacency matrix for this graph. And then a matrix that encodes a lot more information, but is like, I don't know, a little bit less intuitive, I guess, to derive is the Laplacian, which is just defined as each of the matrix elements are -1 if those two vertices are connected. And then otherwise, if the vertex just corresponds to itself, so like, for example, the diagonal, I guess, then it's just corresponding to the degree of that vertex. So yeah, so that's what L equals D minus A means. Basically just D is a degree matrix where it basically only has elements along the diagonal for a regular graph. So we're subtracting the adjacency matrix from that. So let's see, let's just look at the Laplacian for this graph. So I guess starting with the diagonal elements, we just have the degrees of the vertices. So, oh, I should probably explain if you guys don't know. Vertex degree is just the number of edges coming up that vertex. So this would be 2, 2. And then we just like negate the adjacency matrix. So 0. Yeah, so I guess this doesn't like seem like that intuitive of a construction. So I'll just like go over some some motivations for the Laplacian. One of the motivations is that it kind of represents a derivative and that you can measure the changes in I guess like function values based on a node and its neighboring nodes. And this is because the Laplacian is also equal to equals B transpose D, where B is the incidence matrix and D is the degree matrix. Oh, so that's basically maps edges to, so if you have like three vertices and two edges, it would be like a 3x2 matrix, and it maps it has a 0 if that edge is connected to that vertex. A 1 if that, sorry, a 1 if the edge is connected to that vertex. So yeah, this basically like maps nodes to edges, and then edges to nodes, and then nodes to edges back to nodes. Yeah. So yeah, and this is just like, there's nothing like really deep going on here. This is just like based on definition. But that if you want to look into like gradient models and diffusion, that's kind of how that works. And then like a few other things. So I guess the way that the equation is usually utilized is in terms of finding like eigenvalues and eigenvectors. So like we want to find solutions to L minus equals 0. And yeah, I'm probably not gonna write this out. It's gonna take a while. But yeah, basically based on the eigenvalues and the eigenvectors corresponding to like the ordered eigenvalues, we can tell some information about connectivity. So in terms of the Laplacian, the second smallest eigenvalue, which I guess like lambda 2, the eigenvector associated with this value is called the Fiedler vector. But this basically just represents algebraic connectivity, so like how connected the graph is. And yeah, so basically the higher values for the eigenvalues also represent faster changes in node values while traversing the graph. So this kind of goes back to the idea that the Laplacian can model changes in node values. Yeah, hopefully that makes sense. It's not like super related to the rest of this, but I just wanted to like make it seem a little bit less random, I guess. Okay, so this is the first paper I'm going to go over. I hope this paper was really interesting because it I think it like is a good example of showing how you can use properties of graphs and like directly enforce them in like a machine learning model. So basically the idea is that first of all, structured graph learning is an NP-hard combinatorial problem. And this is because as the number of vertices gets larger, the possibilities for the number of edges increases exponentially, right? So if we have like, I'm just gonna like draw vertices, that's the dots. Like if we have this like huge network, there's just like way too many possibilities for what edges can be between them, which is why it's like not easy to determine combinatorially how we can like extract structures for graphic, I guess. Yeah, so the idea of this paper is that they're going to directly enforce structural constraints. This is both directly, I guess, to identify relationships between data. This is how it helps the model. And it's also important for interpretability because it can tell us a lot about what the model is doing behind the scenes. And then I guess this is like this paper in comparison to papers that have done like other things previously that are similar. This paper also implements structure inference and graph weight estimation in a single step, which helps with robustness. Yeah, so in their model, they use weighted edges, as I discussed earlier, to represent the dependencies between the variables, like the feature variables. Yeah, so in addition to weighting edges, the model also is built upon an undirected graph where each vertex corresponds to a variable and the edges are between the vertices if the corresponding variables are dependent on each other. And this is just weighted by that dependence weight, I guess. Yeah, so going back to the Laplacian, this basically just helps us to detect whether a matrix is a Laplacian for some particular graph. So like while this is not the definition of a Laplacian, any matrix that satisfies this property of yeah, I guess like the property is like symmetry, right? Like if two vertices are connected one way, they're also connected the other way. And then I guess, yeah, so like the second condition is based on degree. So the degree of a vertex is equal to the sum of all of the, like, for example, if we look at V2, like the degree of this vertex is equal to the sum of number of vertices it's adjacent to, negated, obviously, because we're subtracting the adjacency matrix. Yeah. And then this next formula is, this is basically their general framework for how they are enforcing the spectral constraints. So they start by maximizing the log of the generalized determinant. Generalized determinant is just the sum of the eigenvalues, I think. And purpose of maximizing this term is so that the graph is well connected and diverse. Because if you think about the determinant, I guess if you're trying to maximize it, it depends based on like the values of the elements of it themselves being maximized, as well as like being like sort of well distributed in terms of like large values. So like not too many like random zeros in places, because that would make the determinant a lot smaller. And then we're also subtracting the trace of the, oh, I should probably explain. So S is the, S, I think it refers to the covariance matrix, which is extracted from the actual data. Covariance matrix basically just shows the dependencies, like the relationships between the features. So it's like, yeah, I don't know if this definition is going to be really helpful, but yeah, basically just think about it as like representing the dependencies of the features in the actual data itself that we're learning from. So the purpose of the trace term is to just like penalize, I guess like very like derivatives off of the actual covariance matrix in terms of the matrix data that we're looking at. And then the last term is, let's see, oh yeah. So this is just a regularization term. I think in the context of this paper, this just enforces sparsity, and then alpha is just the, yeah. But oh, the trace is just like some of the diagonal elements, the elements of the diagonal. Yeah, so in this case, like, yeah, the reason it's a trace is because yeah, I think it's just like kind of a simpler way to detect changes rather than looking at the entire matrix. Because I'm not going to write this out, but like if there's like enough derivatives from the actual data, it'll show up in the trace. Yeah. And then the second part is just spectral constraints. I think I mentioned, oh yeah, so this like ST, this is like the all possible matrices that can be Laplacians for a graph. So we're just restricting to that. And the same thing for like the eigenvalues. So we're basically just saying like, we're only going to allow matrices that can be the Laplacian for a graph. Yeah, so this is, I'm not gonna pretend to understand this equation because I don't, but this is what they're basing the variable dependence structure on. It's something called Gaussian Markov random fields. It's based on like, I think what they do is like they take the inverse of the covariance matrix and like they do some stuff with that. But yeah, it's basically like instead of the covariance matrix, they're just using this. It's kind of it's a cool idea, but I don't think it's like super relevant to go into. Okay, so the algorithms that they derived based off of the generalized framework that we saw a couple of slides ago, um, basically it took the form of either enforcing Laplacian spectral constraints or adjacency. So like spectral constraints either based on like the Laplacian matrix or based on the adjacency matrix or like based on both in tandem. And I think like the results that they got were that um, doing the joint Laplacian and adjacency spectral constraints like had the best results, which I guess makes sense. We're just like giving it more information about the graph. Um, yeah, so I guess we can see like we can kind of like extract a few things from this. Like I'm not gonna define like what every single variable means because it's kind of a lot, but like this is the Laplacian constraint and this is the adjacency constraint, and then we're just like weighting it by like beta over two, gamma over two. So yeah, this is their approach for SGLA, which is the joint Laplacian and adjacency constraints. Yeah, so these are the results that they got for graph learning based on like, in comparison to other models, we can see that the error is a lot less and the F score, I forget what that is, but like the performance is a lot better. So I guess this is like error and then performance. And this is true for each of the algorithms, SGA, SGL, SGLA. I think, yeah, another thing to notice is that like these specific results were tested on like certain types of graphs that are like kind of fit like the nice classifications. So like the SGL was tested on in this image. They like did a bunch of testing. It wasn't just these two results, but SGL was based on a modular graph, which is like kind of related to block decompositions, um, which is like I guess intuitively if you have like we have like a graph like this. It's like this is for graph decompositions, which is like kind of a similar idea. Then you could say like, okay, it seems like the graph is like kind of divided like that, right? So you would like divide these two different blocks. And then this was tested on a bipartite graph, um, which is like this. So yeah, so the performance was quite good on like on this and like a lot more non-trivial variations, like different classifications. Yeah.
What was like, so it's really the closest competitors like the CPO. What was CPO trying to do about maybe cycles?
I have no idea. I don't know what CGL is. I don't know. Does anyone know what CGL is? Okay. Yeah, I don't know. I think I think like none of the other algorithms enforce spectral constraints. I think I don't think CGL was like particularly the best out of the other ones either. I think it like largely depends on what kind of graph it was tested on too. I guess like the reason why these algorithms were the outliers were that they like significantly performed better on like across a bunch of different types of structures. Yeah, so this is the next paper I'm going to go over. This one was a little bit less technical. I kind of wish that they went into a little bit more detail, but yeah, this is just an example of how we can look at graph isomorphisms in order to improve GNN expressivity. In this context, expressivity just means like ability to distinguish between graphs, I guess. And yeah, so the issue in a lot of in like most of GNN graph neural networks is sacrificing invariance to isomorphism. So in general, GNNs are kind of like capped by the WL test in terms of like in terms of being able to distinguish two graphs that are not isomorphic but have like similar substructures. So I guess the idea of this is that they are kind of updating the message passing scheme in order to like account for similar substructures. So yeah. I guess we can see in this message passing scheme, the HV to the T plus one just represents the vertex V at, not the vertex, the vertex think it's H sub B represents the vertex at the time t plus one. And then this is just done by like an aggregating function of like combining all the messages from the previous vertices and then like adding on the new message MB to the t plus one. So yeah, and then the way that they accounted for substructures was basically they built two different features, one based on the vertices and one based on the edges. These are both based on like the occurrences of vertices and edges in induced subgraphs, which, let's see. Yeah, so like if we choose like, I guess like these three vertices, then like the induced subgraph from these three vertices is going to include like this edge and like it's going to exclude some of the other edges because not all of the vertices are in that set. So yeah, sorry, I probably should define that before saying it. Basically, induced subgraph is just like a set of vertices plus the set of edges that are in the graph, and also both of the vertices are in the subset of the table. So yeah, that's how they kind of extracted it structurally. I think like I guess it's kind of interesting here because I guess the claim here is that like induced subgraphs inherently like tell us something like structurally about a graph. And there's like kind of makes me wonder because there's so many different ways that we could induce like similar types of information because there's like so many different methods of graph decomposition. So like, I kind of wonder what would happen if they used a slightly different metric like block decompositions or something like that. Yeah, so I guess this is just like, as I mentioned before, the vertices and edges are based on occurrences in substructures such as induced subgraphs. So yeah, this would just be like the final feature vector that's filled. Yeah, and then the results of this paper was that this new framework, I guess, GSM is significantly more powerful than the previous ones, except in like very specific cases, which are like not super like, I guess they would be like very rare to occur in actual data probably. So yeah. Yeah, so that's pretty much it. These are the two papers that I went over. These are just like a few other papers. I guess the classic gentle introduction to GNNs. And then another paper that I thought was really interesting, but didn't really have the time to like read through in detail is random walks for learning on graphs. There's a lot of like cool stuff out there about graph traversals and like how that can be utilized for learning. And then there's like Node 2-back, which I think is like, also probably pretty classic. But yeah, I guess another thing that I like also kind of wanted to touch on, but like thought wasn't super relevant is just like, so like we talked a lot about enforcing like spectral constraints, but there's also a lot of other ways that we can represent graphs algebraically and like could in theory probably try to enforce different types of constraints. Like this I guess is more like the field of algebraic graph theory, which I'm like a little bit obsessed with at the moment. So that's probably why it's like creeping in. But there's a lot of different ways that we can represent graphs through like not only structures such as like matrices, but also structures like polynomials, which have the power to distinguish types of graphs, especially like graphs like trees and a little bit simpler structures. So yeah, I just thought that would be interesting. I don't know if anybody is like curious about that. But yeah, any questions?